Hello everyone, myself Pankaj Shah, and you will see video of basic electrical engineering. So in today's video, we are going to understand the different type of theorems. And in this theorem, we have already seen the Thevenin's theorem, Norton's theorem, superposition theorem. Now, in today's video, we are going to understand about mass analysis and nodal analysis, which is already discussed in the video of KVL and KCL. But again, I am representing you with some more numericals of KVL and KCL. So basically, nodal analysis is related to KCL and mesh analysis is related to KVL. So let's begin with first the nodal analysis, that is Kirchhoff's current law. So in nodal analysis, let's consider this one diagram. In this diagram, there are so many branches are there. And in all these branches, we have numbered as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and 11. For example, 11 branches are connected. So in nodal analysis, first of all, you have to identify the number of nodes available in your network. In the bottom side of any type of network, there will be a bottom node, and this node is known as the ground node. So its potential is taken as a 0 volt. So you do not have to consider any node on the bottom side. On the top side, you have to consider a node where two elements are connected together. But between the two elements are, if any element is connected, then you have to consider that two nodes separate. But between the two nodes, if no element is connected, then it can be considered as a single node. For example, here, this first, second, third, fourth, and fifth, this all node can be considered as a single node A. And the potential at this node is assumed as VA. Now there is one element, so it will be another node here, and here there is a P node. But again, this all nodes are not separated by any element between them. So this forms a single node, and this node is node B. And the potential at this node is assumed as a VB. Now in KCL, we need to find the voltage of any branch, because its name is Kirchhoff's current law, but we need to find the voltage of any branch by using KCL. So how we can find the node voltages VA and V? So let's begin with the KCL applying at different nodes. Let's apply KCL at node A. So at node A, there are so many elements connected, and we have to assume the direction of current flowing through that element. So let's first talk about this R1. So if you want to find the current flowing through this R1 branch, then the equation should be according to Ohm's law, I is equals to V upon R. So in this first branch, you can see that there is one resistance and there is one voltage source also. And here the potential of this node is VC, that is 0. So how you can define this as VA minus V1 minus Vc upon R1. You can define the current flowing through this branch like this. We will put Vc is equals to 0 later on. Or even if you don't consider this Vc here, then it's also fine. For second branch, it will be Va minus V2 minus Vc upon R2. But here you can check the polarity. In the first case, the polarity was positive negative, so that's why we have taken negative sign. But here already negative sign is there, so negative and negative will make positive, so it will be Va plus V2, because current will flow from positive to negative, that's why, and minus Vc, because Vc is 0. Now, for this two branch, it will be incoming current, so it is minus I1, it is outgoing current, so it is plus I2. Plus, here also another element is connected, that is resistance R3. So for this resistance R3, it will be Va minus Vc upon R3, very simple. Also there is this R4 and it will be Va minus Vb upon R4 is equals to 0. So this is the very basic equation of the KCL or the nodal analysis at node A. If we put Vc is equals to 0, then the equation will becomes very simple. Now, the same figure again we are considering and VC is again equals to 0, and if we put VC is equals to 0 in that equation, then the equation will be like this. So let's apply KCL at node B. So if we apply KCL at node B, then the equation will be like this for this first branch. Now it is 1, 2, 3, 4, 5 and 6 branch is here. So for this first branch, it will be VB minus V4 minus VC upon R6. For this R5, it will be VB plus V3 minus VC upon R5. For this branch, if it is incoming, then it is minus I4. This is outgoing, so it will be plus I3. Here no source is connected, so it will be VB minus VC upon R7 directly. And for this branch, it will be VB minus VA upon R4 is equals to 0. Where this is the particular branch 1, 2, 3, 4, 5, 6, and we know that VC is equals to 0. And if we put VC is equals to 0 in that equation, then it will be very easy equation like this. So we have removed just VC because VC is equals to 0. So now we have obtained equation 1 and equation 2 in terms of VA and VB. So there are two equations and two unknowns. So you can easily find out the value of VA and VB by Cramer's. Let's consider one example. We have to find the branch current for the network shown using nodal analysis where all resistances are in ohm. So here first of all we need to identify the nodes. So here there is one node because 3 branches are connected here, and here another node because 3 branches are connected also here. Let's assume the voltage at this node is VA and voltage at this node is VB, and we need to find the current flowing through each branch. Let's say that current flowing through this branch is I1, current flowing through this branch is I2, current flowing through this 1 ohm branch is I3, and current flowing through this branch is I4. So we need to find I1, I2, I3 and I4. But first of all, we need to find the VA and VB. So for VA and VB, we have to apply the KCL. So now let's apply KCL at node A. So at node A, KCL will be like this: VA minus 20 upon 1. VA minus 0 upon 1 and VA minus VB upon 0.5. So if you solve this equation, then you get this type of equation, and if you separate VA and VB, then it will be like this. Now let's apply KCL at node B. So at node B, it will be like this: VB minus 20 upon 1, VB minus 0 upon 2 and VB minus VA upon 0.5. And if you solve this equation, then you get again the same equation in terms of VA and VB. Now we have two equations in terms of VA and VB. So you can solve this two equation and you get the value of VA and VB as 11 volt and 12. So VA is equals to 11 volt and VB is equals to 12. If you want to find the current through different branch, then what you have to do is, if you want to find the first current I1, then VA is equals to 11 here. So it will be 20 minus 11 upon 1 because I is equals to V by R. So it will be 20 minus 11 upon 1. So this is the answer of first. If you want to find the current of this branch, then VA is 11 and VB is 12, and the actual direction of current should be from VB to VA. It will be 12 minus 11 upon 0.5. If you want to find the current flowing through this I3 branch, let's say, so for this branch it will be 11 minus 0 upon 1. For this branch it will be 12 minus 0 upon 2. And for this branch it will be 20 minus 12 upon 1. So in this way you can calculate also the current flowing through each branch. But basically here the nodal analysis states that you need to find the node. So this was all about the nodal analysis. Now let's see the mesh analysis. So mesh is a closed path which does not contain any other closed path within it. So for this figure we can see that there are 3 closed paths. So there are 3 meshes available in this diagram. And mesh analysis is generally used to find the current flowing through any element. So first of all you need to identify the number of loops. How many loops are available in this equation, and the number of loops will be always equals to the number of equations that we have to find out. So apply mesh analysis, that is the KVL, to each loop available in that network. And if we apply mesh analysis to the first loop, that is A, B, T, A. So if we apply mesh analysis to this loop, then it will be IR, because we have to do KVL, that is the addition of all voltages. So the addition of voltage across this element will be I into R. Current flowing through this branch is I1 is flowing through this mesh, so I1 is flowing in this direction, but I3 is opposing it, so it will be I1 minus I. For this branch, I1 is flowing downwards and I2 is flowing upwards, so it will be I1 minus I2 for this branch. And this V1 is source alone, so negative to positive, so it will be negative V1. You have to take the destination, you have to take the starting sign, that is negative to positive, so you have to take negative sign, and it's equals to. If we apply KVL to the second branch, then if we start from this R3 resistance, then it will be I2 minus I3 into R3. For this branch it will be plus V2, for this branch it will be I2 minus I1 into R2. If we apply KVL to the third mesh or the third loop, then it will be R4 I3, because this is a single element, no other current flowing through it. For this R3 resistance, it will be I3 minus I2. And for this R1 resistance, it will be I3 minus I2. So we obtain three equations from this mesh analysis. If we just separate this three equation in proper form, then we get the answer of I1, I2 and I3 very easy. Let's say this is one example of three meshes. So many sources and resistances are connected and three loops are there. So first of all, we have to apply KVL or a mesh analysis to the first loop here. This is loop 1. Okay. In this loop, if we start from this 8 ohm resistance, then IR will be 8 into I1 minus I3. For 20, it will be 20 into I1 minus I2, because current flowing through this branch is I2. And minus 10 plus 50 into I1 will be there. Here 50 I1 is not mentioned, but it will be there. So if we solve this equation, then we get the answer like this. If we apply mesh analysis to the second loop, so for this second loop, it will be 10 I2 minus I3. For 25, I2 occurs only, I2 only flows through it, so it will be 25 into I2. And for this 20, it will be I2 minus I2. And if you solve this equation, then you get the answer like this only. Now apply KVL to the third mesh. So for the third mesh, if we start from this battery, then it will be plus 20. For this, it will be 4 I3 plus 4 I3. For this 10, I3 minus I2. And for this 8, I3 minus I1 will be. And if we solve again this equation in terms of I1, I2 and I3 and equal to constant, then it will be like this. So the equation will be having the proper form, that is I1, all I2, all I3 is equals to constant is this form. And if you can divide that equation by any number, then you can also reduce the complexity of that equation. So now we have three equations. And this three equation can be solved by the Cramer's rule. For that, you have to use the matrix form. So we have written this equation in matrix form like this. And if you want to find the value of I1, I2 and I3, then you have to use the Cramer's rule. But first of all, you have to find the value of lambda. Lambda is nothing but the coefficients of I1, I2 and I3. In this case, 33 I1 minus 20 I2 minus 8 I3 was in the first equation. These are the coefficient of second equation and these are the coefficient of the third equation. And if you solve this delta, then you get the answer of delta. Now, if you want to find I1, then you can find I1 first of all by calculating delta 1. So delta 1 can be calculated by, you have to replace the first column of the delta by the coefficient on RHS. So to find the I1, you must need to find delta 1, or you can say D1. And for that, you have to replace any column of this matrix by the outer coefficient. So for finding the I1, you have to replace the first column. To find the I2, you have to replace the second column. And to find the I3, you have to replace the third column. So that is known as the D1, D2 and D3. And if you want to find the current I1, then the answer will be D1 upon the D. I2 D2 upon D and I3 is equals to D3 upon D. So in this manner, you can calculate D2 also, and you can calculate D3 also, and you can find the values of I1, I2 and I3. So in this way you can apply mass analysis to any type of circuit. So in this video you have seen mass analysis and nodal analysis with numericals. Thanks for watching this video. Stay tuned.